Okay, so this will be the recording for the second lecture. And this lecture will focus on linear regression, the general linear regression with multivariate input. So let's look at the training data. We have n observations or n training examples. And for each training example, there are p predictors, and we denote them xi1 to xij to xip, where j indicates the variables or predictors, and p is a number of predictors. So p stands for predictors, and n stands for the number of observations. And yi is a response. Although we can also generalize yi to multivariate, in this lecture, I will mainly focus on the situation where yi is still univariate. So the generalization from the simplest regression to this multivariate regression is only about this xi. So xi stands for the vector consists of xi1 to xij to xip. So we generalize xi from a scalar to a vector. So that's the only difference. And this n and p is standard notation in a linear regression model in statistics. And in the traditional statistics, n is much bigger than p. But in modern statistics, the so-called high-dimensional statistics, and also in machine learning, often we study the situation that p can be much greater than n. And p consists of some variables, but we may also consider those variables as features that are computed from the raw input variables. Okay? And that's a more common view for modern machine learning. So those xij, they are features instead of the original raw variables. Although how to design the features and how to learn the features can be also an important issue. And this is again in the supervised learning framework, where this yi is considered as a supervision, so that the model tries to learn to predict yi based on xi. So this is a row vector, and we call this as xi transpose, actually. So in general, the supervised learning is to learn a mapping from input to output. More specifically, our linear model is as follows. So yi is xi1 times beta1 plus xij times beta j, and then plus xip times beta p, and plus ei. So ei, again, is error or residual. So here I want to single out the linear structure so that we denote Si, which is a linear score, to be xi1 beta 1 plus xij beta j plus xip beta p. So this linear structure underlies both the linear regression and also the logistic regression, and later neural network or some other machine learning methods. So we always have this linear structure. And you can even interpret this linear structure as a part of a neural network, where each input is a neuron, input neuron, the activity of a input neuron. And then Si is the output, the activity of the output neuron. And this beta 1, beta 2, beta j, and beta p, those are interpreted as synaptic connections between neurons, or the connection weights. So that's the interpretation. And this is just a linear part of a neural network. And there's only a single layer of a neural network. And later we will see that the full neural network actually is based on this structure. So this building block, you only need to compose those structures together. And also you can insert a nonlinear rectification or nonlinear transformation after you get SI. This nonlinear transformation is often given, as we will see in the logistic regression. So still, we only need to learn those beta coefficients, and you can interpret the beta coefficients as the effect for Xij on Si. Okay, so this linear structure underlies most of the machine learning methods. One complication is the intercept term or the bias term, beta 0. So we can also write Si as a beta 0 plus Xi1, beta 1 plus and so on. Okay. But if you consider or you expand your features so that you include Xi0, and you always set Xi0 to be 1, then the coefficient for Xi0 can be interpreted as an intercept term. So this intercept. Sometimes people also call this a bias term. So which means after you compute the neural response, right, neural output response, you then add this beta 0 as a bias term. So this bias term comes from this neural network language. Okay, and let's take two types of treatments for this linear regression model. So in today's lecture, I will first give you a treatment based on row vectors. And then after that, I will give you a treatment based on column vectors. Okay, and also we will see the two treatments actually agrees with each other. So the row vector treatment is maybe more general. It can be applied to logistic regression and other machine learning models. And vector treatment is more specific to a linear regression model, give us a geometric interpretation for linear regression, which is also quite revealing and important, I would say. Okay, so we define Xi, the ith training example. So this row vector, we define this as Xi transpose. So when we talk about vectors, often we just consider a vector to be a column vector, but this is a row vector, right? So we need to transform this. So this transpose, Xi transpose. So that is Xi is a vector consists of Xi1 to Xij to Xip. And correspondingly, we can also write beta to be a vector beta 1 to beta j to beta p. Okay, and then for this row, you can also write Si to be the inner product between Xi and beta. So this Xi beta. So Si equal to the inner product between Xi and beta. And we can also write this as Xi transpose times beta. So this is how we write the inner product. And in machine learning language, especially in support vector machine, linear support vector machine, people also write Si to be Xi times W plus B, where W denotes or stands for weight. So those beta are considered as a connection weights. So in some of the machine learning models, such as support vector machine, people use a W for beta. So this will be the inner product between Xi and the W plus B. B stands for the bias term, which corresponds to beta 0 here. Okay. For the linear regression, let's go back to the linear regression. We can then write EI to be YI minus SI. So that is SI is the prediction based on this linear model. And we want to use SI to predict YI and with error EI. So EI is YI minus SI. And you can see that SI is computed based on beta, for different beta, you are going to have different SI, right? So therefore, the way we estimate beta is to use the least square method. Let me try to fix it more slowly. So we use the least square method again as a method invented by Gauss. So the least square method is 1/2 summation of EI squared, and EI is YI minus SI. SI is XI transpose beta. So this function is still a function beta. And this is the loss function that we are going to use for logistic, for linear regression. And later, we shall modify the loss function to for the logistic regression. And for this particular simple loss function, we can compute the derivative of this loss function with respect to beta k, for k from 1 to p. And here I use generic j as a indicator for a particular beta, right? So j from 1 to p. But because often we write this as summation, right? We write this as a summation for j from 1 to p, xij times beta j. So when we take derivative, we better use a different notation. So now I use k. So k is keep flowing. Okay, sorry about that. So k, what's happening? Move slowly. Sorry, I have to master this type of view. Okay, so slowly, and then in order to compute the derivative of this loss function with respect to beta k, we can use the chain rule. So that will be summation I from 1 to n, right? And then we have this EI. So well, the derivative for something squared is 2 times this something, right? And we have 1/2 here, so they get cancelled. So often, as I said, we put 1/2 in front of a square term. And then we will have EI, right? EI. And then we use the derivative partial EI over partial SI. So EI equal to YI minus SI. So we use the chain rule to go through the chain of dependencies, and then partial SI over partial beta k. Okay. And now you see that when we compute this derivative, we start from EI because we have summation EI squared. So this summation EI. And then we go through the chain of these dependencies. And then you can treat this as a simplest example of error. You have this error here, and then backpropagation. You go through this backpropagation, which is basically just another term for the chain rule for this type of models. Okay, so if you use the graph here, so you have the E, right? This SI is used to predict the YI. So you get the error EI, and then you go back. So from the EI, you go to SI, and then you go back to each of the beta k. So when we compute the derivative with respect to beta k, then we use this chain rule formula. And now let's do some concrete calculation. So this summation I from 1 to n, EI, and then the derivative of EI with respect to SI. So EI equal to YI minus SI. So we just have negative sign here. And then we compute the derivative of SI with respect to beta k. So SI is summation xij times beta j, right? You sum them over. And when you take derivative with a particular k, then it will be xik, right? Because all the other terms are not related to beta k. So only the k's term, xik times beta k, contains beta k in this summation of xij times beta j. So only the k's term. So that's why I use k, because si equal to here, this is a summation. When you compute the inner product, it's a summation j for xij times beta j, right? But only the k's term has anything to do with beta k, and the k's term is xi k times beta k. So the derivative will be xi k. And this is true for all k from 1 to p. You have this equation. And this is an important equation because this is the root for us to then express it in two different ways. In terms of this row vector treatment, so when we compute the derivative for loss function with respect to beta k, and then we can define the derivative of the loss function with respect to beta to be a column vector, because beta is a column vector, p-dimensional column vector. So we can also define the derivative as a p-dimensional column vector. So this is a generalization of the notion of univariate derivative to multivariate version. And later, we will see that this is actually called a gradient. So it tells us the steepest direction to increase or decrease a function. That's the reason we call this a gradient. I will talk about this later on, but for now, let's just look at this derivative of this gradient, which consists of the k elements. So each one is the derivative with respect to beta k, and you let k go from 1 to p. So you get this p-dimensional vector. And now let's look at what it is. So this is negative summation because each element, right? When you sum over a vector, you only need to sum over each element. So this will be summation xik ei, right? Well, ei, and this for k from 1 to p. Okay, and then this is negative summation I from 1 to k, 1 to n. Sorry, this I from 1 to n. And then you can see that this k from 1 to p, right? K change, but if you multiply this by ei, ei doesn't change for k from 1 to p. So therefore, you may move ei out of this vector because now this p by 1 vector, ei is 1 by 1 scalar. And when you have vector times the scalar, you just multiply this scalar to each element of this vector. So the two equal to each other. Okay. And then in this way, we can write this derivative, this vector, to be summation I from 1 to n. And you see this vector for k from 1 to p is exactly xi. Remember that the xi transpose is a row vector, so xi itself is still a column vector, and xi times ei. So xi is p by 1, and the ei is 1 by 1. So the final result is still p by 1, which agrees with our definition for the derivative. Okay. So in my lecture, I try to make the transition from scalar to vector, or from univariate to multivariate, to be as simple as possible. In fact, when we look at the multivariate version or matrix version or vector version, it is really a packaging. You just package all those individual elements into vectors or matrices so that the final form is still very similar to the univariate form. And in fact, this is also the derivative for the univariate version. In the univariate, you are going to derive the same thing as we did in the last lecture, right? Summation xi ei. And at that time, xi is a scalar. Now it becomes a vector. So it is a very simple generalization. Okay, and then we can set the derivative to 0 so that we can solve for beta, because ei is yi minus si, and si is a function of beta. So we can solve for beta by plugging this substitution for beta. Okay, so let me move. Okay, good. Sorry about that. I think, yes, this is what we have for the next page. Okay, so this page, this PDF somehow, I want to use the full screen view, so I need to navigate this one. Okay, so now we have our estimation equation. Remember that this ei is yi minus xi transpose beta, right? This is how we define the EI, which is error. And the error, so SI is yi minus SI is xi transpose beta. So we just plug in to do the substitution. And then we have the summation xi times yi minus xi transpose beta. And we set this to 0 in order to get the derivative, right? So to get the solution for beta. Okay, so now you see that we can separate these two terms. So this summation xi yi minus summation xi and xi transpose beta, and then this equal to 0. So here xi transpose beta just come from this term, okay, a negative sign here. And now we can look at this. So we can write this, actually, beta is the same over all I, right? So you can write this as summation xi transpose times beta. Okay, so this guy can be written in this way, and this should equal to summation xi yi. So now let's look at the dimensionality. So xi is p by 1, and xi transpose is 1 by p, the row vector. So p by 1 times 1 by p, this is p by p. In fact, this is xi times xi transpose is a multivariate generalization of xi squared, which we derive in the simplest regression case. Okay, so this will be summation xi transpose. Okay, and then we have this summation xi yi. So xi again is p by 1, yi is a scalar, 1 by 1. So this final result is still p by 1. So now you have this squared matrix, p by p squared matrix times beta, which is p by 1, equal to a vector, which is also p by 1. So therefore, you can write your beta hat to be the inverse of this p by p matrix, assuming that it is invertible, and times this p by 1 vector. So this is your least square estimate, and this is the general situation, for the general multivariate situation for linear regression. So it generalizes the simplest regression. We start from the simplest regression, and we then generalize xi from scalar to a vector, and then we get this result. So this is a very important result, and probably the first non-trivial machine learning result we have. And we derive this beta hat as the least square estimate of beta, estimated from the training data. So Gauss invented the least square method, but Gauss wasn't just happy to write down this least square loss function as a heuristic. He actually want to justify it or motivate it. So what's a deeper reason for us to use least square method? And then Gauss essentially proposed this maximum likelihood interpretation. Although maximum likelihood was developed by Fisher, who's the founder of statistics, but Gauss actually implicitly, at least, justify or inspire the least square or derive the least square method as a special case of maximum likelihood. So why do we care about the maximum likelihood if we already have a least square method? The reason is that if you can find a deeper principle, such as maximum likelihood, which is deeper than least square method, then this deeper principle may be more applicable to more general situations. So that later on, when you study, for example, logistic regression, you can still use the maximum likelihood estimator, even though least square estimator may not be that good. Okay, so that's why we always seek the more general principle or deeper principle in order to cover more broader examples or applications or problems. So the idea is that we assume that EI follow a normal distribution with mean 0 and the variance sigma squared. A normal distribution is like this bell-shaped curve. And for this one, it's centered at 0. And if we go 2 sigma, 2 standard deviations away from the center, we cover 95% of the probability. But intuitively, you can imagine that on this line, you have a lot of points. Okay, you have a lot of points, and they scattered around, and around zero. And there's more points near zero than the points far away from zero. So you can always visualize a probability density function as a cloud of points. Even in the multivariate situation, you can still visualize the probability density function as a cloud of points, so that the density tell you how dense the points are populating this whole region. Very much like when we talk about, say, the population density of LA, we just count the number of people in LA and divide by the size of LA, or the density at UCLA. We count number of people at UCLA at a certain moment and divide this by the area, right? So this is the notion of a density, how densely packed those peoples are at around each point. And so whenever you try to visualize or try to understand a density function, always think about a cloud of points and then count the number of points around each area, each neighborhood, and divide by the size of this neighborhood. So that's the basic idea of density. But given this density, then we know that this yi, because yi is SI plus EI, right? So yi, so SI is a constant, so it's not random. So yi given SI will follow normal center at SI and variance sigma squared. So because EI is a normal 0 sigma squared, so if you add SI, then SI becomes the center or the expectation or the mean. So this distribution is, we basically assume that yi given SI, which is computed as xi transpose beta, follow a normal distribution with mean SI and the variance sigma squared. So SI become a parameter of this distribution, this density. In particular, if you write down this density, it will be 1 over, sorry, there should be 1 over square root of 2 pi sigma squared, and then E of negative yi minus, so this is SI, and squared outside, the square is outside, divided by 2 sigma squared. Okay, so that's the density, probability density. So it's centered at SI, and if you imagine under hypothetical repeated sampling, you are going to have a lot of yi, right, hypothetically, and then most of the yi will be in this range 95% of the times, but sometimes go out of this range. Okay, and from here we can write down the likelihood for beta to be the probability that we observe yi given SI, and for all the whole data set. And we assume that the observations of those training examples are independent of each other. So their joint probability will be the product of those individual probabilities. So we just multiply them together. So this is yi given SI, and remember SI is xi transpose times beta. Okay, so this is a likelihood function. And the maximum likelihood principle is that we want to find the beta to maximize this likelihood, so that under this beta, then the probability that we observe those yi is maximized. So that is, you gave the most plausible explanation to your observations. So that's the basic idea. And if we want to do real computation, then this product is not very convenient. Often we just take log. So that will be the log of likelihood as a function beta. And then this summation I from 1 to n log of each of this probability. And the log of this one, given this density, will be negative. We have negative yi minus, so this is SI and the square outside, yi minus SI squared divided by 2 sigma squared, and then minus the log of 1 over this guy, which is 1/2 of log 2 pi sigma squared. So this, suppose we know sigma squared, then this is just a constant, right? And then we have negative 1 over 2 sigma squared. We move this out, and summation yi minus SI squared minus n times this guy, which this constant has nothing to do with SI, only has nothing to do with beta, only SI, which is xi transpose beta, depends on beta, right? So therefore, for this log likelihood, there's negative sign here. So in order to maximize this log likelihood, you only need to minimize summation yi minus si squared. So this gives you the least squared method. So that is, least squared method can be considered as a consequence or a special case of a maximum likelihood method, where we assume a normal distribution of yi given si. Okay. So that justifies the least squared method. And as I mentioned, this is a very useful exercise, because later on, when we have new data, for example, in the logistic regression, we still use the same principle of maximum likelihood, so that we can derive our objective function for estimating beta. And for the logistic regression, this probability in logistic regression, yi is either 0 or 1 as a binary random variable. And then this si, instead of defining the mean parameter of the normal distribution, it also defines the mean of yi, except that this mean of yi for the binary situation will be the probability that yi equals 1. So si defines or determines what's the probability yi equals 1 through a nonlinear transformation, the so-called sigmoid transformation, as we will see in the next lecture. So this part is really foreshadow the next lecture, so that we can make a smooth transition from linear regression to logistic regression, so that in the logistic regression, instead of we'll continue to use the least square method, which is not very accurate, we now use maximum likelihood method, but still follow the same principle. Okay, so that's the purpose of this part of the lecture. We basically try to make our transition to logistic regression easier. Okay, but also this is indeed how Gauss justified his method of least squared, and then that's the reason this distribution, the normal distribution, is also called Gaussian distribution. Okay, so now let's move on to see if we get this one. Okay, let me be more careful here. Yeah, I think I should move to this part. Okay, very good. So now we start this column vector view. So we can also treat the linear regression model based on the column vectors. However, for logistic regression, we shall not focus on column vector. We will mainly focus on the row vector point of view. Column vector point of view is mostly for linear regression. It gives us a very clear geometric interpretation. So for the column vector, so each column represents a variable or a feature, and we write this column vector, which is n-dimensional vector, as x sub j. We may use capital X for the column vector, where we still use lowercase x for the row vector. And then we can use this big X as the whole matrix. Sometimes people call this as a design matrix, because sometimes people design the value of xi, especially in the so-called experimental design. But in any case, this X will be a n by p matrix. So it consists of this p column vectors. We put the p column vectors together, we get this matrix. Okay, and similarly, you can let y to be this vector of responses or vector of outcome variables. Remember that our model is yi equal to xi1 beta 1 plus xij beta j plus xip beta p, right? For each observation I and plus ei. So if we package them together, we will have this y. So we package yi together, we get a y vector. And this one will be x1, right? We put them, make them together, you get x1 beta 1 plus xj beta j plus xp beta p and plus e. Again, for the matrix multiplication convention, so we put this scalar beta j on the right, because this is xj is a vector, n by 1, beta j is 1 by 1, so the result is still n by 1. But sometimes people put the coefficient in front. This is just for convenience. But if we want to follow matrix multiplication rule strictly, we need to put beta j on the right-hand side, right? So this xj times beta j. Okay, so here comes a very important and also very useful trick for dealing with like things like that. So that is now, if you want to further package this this form, and then you can pretend each of xj as a scalar, as a number. Okay, and then this is in the form of inner product, right? So that you can write this as a row vector for x1 to xp times a column vector beta 1 to beta p. Okay, so here we pretend each xj to be a scalar. So this is almost like a matter rule when you deal with vector matrix type of things. So when you try to package things together, and then you can treat each symbol or pretend each symbol to be a scalar. And then you can see the result very easily, so that you get this one, you get this row vector times column vector, you get this inner product. And then you realize, sorry, this is not reduce, this is realize. Then you realize xj as a vector, okay? And then you put those vectors together, you actually get a matrix, just like what we have here. This X matrix consists of all those vectors together. So all those vectors together got a matrix. And then you can write this as X matrix, and this is a beta vector. So X is n by p, beta is p by 1. So the final result is n by 1, and plus e. E is a collection of ei. So it is a n-dimensional vector, n by 1 vector. Okay, so that's how we write things in the vector and the matrix form. Okay, and then if you look at the loss function, the loss function continue to be 1/2 summation ei squared, sum of squares. And then we can write this as 1/2 of a square norm of this e vector. This e vector is here. This is our e vector. And remember, when we take the derivative with respect to beta k, we get a negative summation ei xik. Okay, that's in our previous row vector treatment. So maybe let me go there, see if we can find it. Okay, so that's how we derive it. You see, this is summation, right? Ei squared, and we take derivative ei and the chain rule, and then we get negative ei xik. Okay, so that's where we derive it, and we continue to use this result. Okay, so that you now have try to find it. Okay, so that's where it is. So we have this derivative with respect to beta k, right? This is negative ei xik. And then you can write this as an inner product between two vectors. So this is e vector, and this is xk vector, the k is column. Okay, and this only means that for each vector, this e is perpendicular to xk. And now, very similar to the univariate case, you can also consider this as a projection. You project the y vector, actually the y vector should end here. So you project the y vector to the subspace spanned by these x vectors. Suppose we only have two variables, predictors, x1, x2, and then the matrix x times beta will be x1 beta 1 plus x2 beta 2. So beta 1, beta 2 are the coefficients of the two vectors. So geometrically, this x beta, which is x1 beta 1 plus x2 beta 2, lies on the subspace of the plane spanned by these two vectors. So these two vectors, x1, x2, span a plane, which is subspace of this n-dimensional space. And then we minimize the norm of E, the length of E, which means we project, so this Y should end here. We project Y onto the space, subspace spanned by x1, x2. And this is the projection. So that's a least square projection. Okay. And because it is a projection, so that E is perpendicular to this whole subspace, which means it is perpendicular to all those x. So E is perpendicular to each of xk. So that's a geometric interpretation. Okay. So now we have this E is perpendicular to each of xk, and the inner product can be written as a xk transpose times E. So this equal to 0, and this is true for k from 1 to p. Okay, so this is, we just rewrite the inner product and set inner product to 0 because the derivative should be 0, and geometrically that means E is perpendicular to each of xk. So we write this as xk transpose times E equal to 0. And now we do the packaging. So again, we can pretend each xk is a number, or xk transpose as a number. So for k from 1 to p, so this become a p by 1 vector, where each element is xk transpose, and then times E equal to 0. You can also pretend each E to be a number, and then this number times this vector, you just multiply this number to each element so that you get xk transpose E equal to 0. So this is how you do the packaging. And then you realize xk is actually n by 1, a vector, so that xk transpose is 1 by n row vector. Okay, and then you put xk on top of each other. This is simply the transpose of the X matrix, because X consists of all those column vectors, right? X1, xk to xp. If you transpose them, it will be x1 transpose, x2 transpose, xk transpose, and so on. Okay, so that is, you write this one, this guy become a transpose of X, the whole X matrix. And this E, you realize this E is also a n-dimensional vector. And then you have this X times E equal to 0, right? Equal to 0. And the E, as we showed before, E is Y minus X beta, because Y equal to X beta plus E. So E equal to Y minus X beta. So therefore, you have X here, X transpose, and then Y minus X beta equal to 0. Okay, and then you can write this as X transpose Y minus X transpose X times beta equal to 0. And then you have X transpose X beta equal to X transpose Y. So beta equal to X transpose X inverse X transpose Y. So this is the result we derived for the column vector treatment. And it is even simpler for the result than the result for the row vector treatment. But these two are actually equivalent to each other. The reason is like this. Okay. So remember that this X transpose. So X transpose is what you have for if you look at this xi. So xi, if you look at the original X matrix, say this is your original X matrix, right? So each row is your xi transpose. And if you transpose it, then this becomes X transpose. And then each column is xi. So you have n columns now if you transpose it, and each column is xi. So therefore, X transpose is actually just x1 xi to xn. Okay, you see if you transpose it, and then xi transpose. So this each row is xi transpose, and if you look at them together, this is x, right? So therefore, X is consists of all those Xi transpose, and X transpose consists of all those Xi. Okay, so now if you want to compute X transpose times X, you just write out them in terms of Xi, and then you get this Xi and then this Xi transpose. Again, you pretend each one to be a number or to be a scalar, then this is simply the inner product, summation Xi times Xi transpose. Similarly, you have this Xi here, and then for Y here, X transpose Y. If you want to compute X transpose Y, so Y is here, Y1 to Yn, right? So again, it's inner product by pretending each one to be a number. So this becomes summation, say Xi times Yi. Okay, and then this beta hat can be read as a summation Xi transpose inverse, and then times summation Xi Yi. So this is equivalent to the row vector view. Okay, the same thing. Okay, so therefore we derive basically the same result. So for the homework, I asked you to prove that beta hat equal to this one. So you can go over the row vector view, okay, to prove this result. I also asked you to prove in terms of X transpose X inverse, X transpose Y. So you can either go over the column vector view to derive that result. But you can also just simply argue or explain that this guy equal to X transpose X, as we show here. And this one equal to X transpose Y, as we show here. Okay, you can also do that, so that you don't have to repeat the column vector treatment. Okay, you only need to give the row vector treatment to get this result, and then explain that this is X transpose X, and this is X transpose Y, to prove the result based on the X matrix and the Y vector. Okay. So you can also do that. So therefore, let me repeat, for the homework, you can either go over both the row vector treatment or column vector treatment, or you can just go over the row vector treatment and explain that it is the same as the result of X transpose X inverse, X transpose Y. Okay, you can go both ways. But here, I again want to emphasize that whenever you want to package those symbols into something like a vector matrix, you can always pretend each symbol to be a scalar, to be a number, so that you can easily get the result in terms of, say, inner product or some vector times a constant, something like that. And then you later recover the original meaning of the symbol and show that they become matrix or some other things. So this is a way you deal with the matrix and vector. Okay, so this is the linear regression. So we deal with linear regression, and for logistic regression, it is also supervised learning, and that's maybe more relevant to machine learning, especially for classification or pattern recognition, where Yi is not continuous, like a sans height, this type of thing, but rather it is a like a binary. So for binary class, for example, Yi may be 0 or 1, where 0 means negative, 1 means positive. For example, I give you a lot of images. Some images are faces. So you can then do a classifier, right? Face or non-face. So this is actually the face detector on your cell phone. So this is a classification problem. And we still want to use a regression model. So we still want to keep this linear structure. So the score SI equal to xi1 beta 1 plus xij beta j plus xip beta p. We still want to keep this linear structure because this is very simple and very easy to deal with. So we can still write this xi transpose beta. So still we have this linear regression. However, for logistic regression, Yi is a binary, so that we need some extra nonlinear transformation. For example, there is a perceptron model, perceptron, T-I-O-N, perceptron model, where we predict the yi to be the sign of ISI. So that is, if this score is positive, we say, oh, this is a 1 or this positive. If the score is negative, we say this is negative or this is 0. Okay, so that's we have the actual. This is called perceptron. But then we can soften it. So instead of just predict yi, we can predict a probability that yi equals 1. So this pi, we let pi to be the probability. PR stands for probability of yi equals 1 given SI, this linear score. And we let this to be a sigmoid function, sigmoid of SI. So this sigmoid function is defined formally, more formally as e to the power SI divided by 1 plus e to the power SI. So this function transforms a continuous score from negative infinity to infinity into something like a probability from 0 to 1. So you see, if SI go to negative infinity, this goes to 0, this goes to 0, so the whole thing goes to 0. But if SI go to positive infinity, this become infinity, this become infinity. So 1 doesn't really count, right? We can ignore it. So this go to 1, and it is a monotone function. So at 0, when SI equal to 0, so this is 1/2. Okay, so it increases from 0 to 1. So this is a nonlinear transformation. And this nonlinear transformation is quite important in neural network. It is also used in the neural network where we have these linear structures with learnable parameters beta, but we also have this nonlinear transformation, or sometimes people call this as nonlinear rectification. Okay, so in any case, so here we have this nonlinear transformation of the linear score, and then this pi predict yi, right? So supposedly, if yi equals 1, then our learned pi based on the learned beta that give us SI, which is xi transpose times beta. So pi should be close to 1. And if y equal to 0, then pi should be close to 0. So we can continue to use the least squared loss function to learn beta. And indeed, in the early days of neural network, people use least square. But this is not as accurate as the maximum likelihood. So that is, in this logistic regression, least square method cannot be derived from maximum likelihood. So it is not a special case of maximum likelihood as in the linear case. So therefore, instead, we use a deeper principle. We use maximum likelihood, which is still summation of this log likelihood. It will be the log p of yi given SI. So this one shares the same form of the log likelihood for the linear regression model that we derived before. But the exact formula for this log p yi given SI will be different. So in the next lecture, we shall derive the exact formula, and also we shall study how to optimize this objective function in order to estimate, to compute beta. So for logistic regression, we cannot find a closed form solution for beta. However, interestingly, we can use an iterative algorithm so that each iteration is still a least square problem. We can still solve a least square problem as a surrogate for this maximum likelihood objective function. Okay, I think we may stop here. That completes the first week for the lectures.